All right, so looking at number 10, we said, I think, let me ask you this. Did y'all like the guy I told you about, Evan, his little method of replacing it, or did you rather do the algebra? Okay, I kind of like the replacing. The only downside of the replacing is you got to make sure you select the right thing. If you select the wrong thing, you're going to be doomed. Like I see people all the time that come in here and go, oh, 5, 5, right here, must be this. But what's wrong with this thing? It's not the original. The original is 5 minus. Okay, now let's try this. What's wrong with this thing?
The original isn't 5 minus 2 times 11.
The original is not 5 minus 2. So there's actually a weird thing going on here. You know, like we did some problems yesterday where we had a random number out front like 7 or 11 or whatever, and it was obviously different. But the pattern here is 5 minus 2 root, 5 minus 2 root, 5 minus 2 root. Or you could argue root 5 minus 2, root 5 minus 2. But you can't, that negative and that 5 are messing with you. Are you with me on that? Yes, no? So on this problem, not only is the 5 not fitting the narrative because there needs to be a 5 minus 2 there, that 2 isn't there. So really, when you look at this, you have to look at it from the standpoint of, okay, I don't even see something repeating with that 5, so let's eliminate that for a second. And then I don't even see anything repeating with that negative. But with that is the repeating part. So that's the part that I'm going to be working with. I need to get rid of that 5 and that negative. Now, who in here decided they were just going to, like, whenever there was something on the outside that was different, that they were just going to do the part they liked and then go back and add it or subtract it or whatever at the end? Who's going to do that? One? Okay. Well, if that's you, then you're going to do this, and when you're done, you're going to go 5 minus whatever you got. All right? Totally fine. Just remember to do it. Now, does that make sense? Okay, if you're not of that mindset, again, I'm going to name this x, right? And then I'm going to subtract the 5. That gives me this thing. So in my opinion, this is probably one of the trickier ones on here. And I subtract that 5 and I get x minus 5. Are you with me? Now, right here, when I get rid of that, this is still not patterned, is it? It needed a negative 2 and it didn't have it. So I'm going to multiply through by a negative also. And that negative gives me negative x plus 5. Now, I see something that actually has a pattern to it. So on this particular one, it actually took 2 steps, unlike the examples yesterday where it took 1. And it really didn't even look like it needed any steps at first. Because it kind of looked like if there had just been a 2 right there, everything would have been nice, neat pattern, but there wasn't. So you had to make it get to the point where, like, okay, now, if all of this is negative x plus 5, where do you see this repeat? The second, so this is the first root 5 minus 2. This would be the second root 5 minus 2. So what is all of this equal to? Negative x plus 5. Now here's where you got to be careful. Is it the square root of 5 minus 2 minus negative x plus 5? Or minus x plus 5? Or is it 5 minus 2 times negative x plus 5? It's got to be times, because this is 2 times this. So you got to go 2 times negative x plus 5. Did that make sense? And then you're almost home free from here. At this point, I probably want to clean that up a little bit. And you could do it after you squared it, but that gives me 5 positive 2x minus 10, or 2x minus 5, right? So all of that right there ends up being 2x minus 5.
Can you square it first?
You can. Yeah, if you want to square it and then simplify it, you're going to end up with just a 2x minus 5. If you want to simplify it and then square, you're going to end up with a 2x minus 5. Either way, that's fine. Over here, I end up with x squared minus 10x plus 25. And at this point, you should be in pretty good shape. Add a 5 is 30. And I'm pretty sure most of these don't work. The answer suggests that the quadratic formula is not going to help you. So right here, I would go negative b plus or minus b squared is 144 minus 4 times a times c all over 2a. And you get 12 plus or minus 144 minus 120 is 24. Square root of 24 is 2 root 6. And when I divide that by 2, I get 6 plus or minus root 6 because the 2 cancels. And then for those of you that are wondering about the plus or minus, we'll go ahead and talk about that. When I look at this problem, I look at this as two options. It could be this answer, the plus answer, or it could be the minus answer, right? Now, I know that root 6 is ballpark what? 2 point something. And again, how do I know that? Because root 6 is in between root 4 and root 9, which are 2 and 3. So root 6 has got to be something like 2-ish. I'd probably lean towards like a 2.4 maybe because it's a little closer to the 4 than the 9, right? So if it's about 2.4, what would this be approximately?
8.4.
About 8.4, and this would be about what? If root 6 is about 2.4. About 3.6. So the question is it that or is it that? Well, when I look up here, I go, I know that when I take this square root of all that junk, it has to be positive. It's either positive or imaginary, right? It's got to be positive. So on this. So if it is positive, what happens when you take 5 and subtract a positive number? It's got to be smaller than an 8.4. So in this case, I go, well, can't be that, must be that. So that's how I'm going to determine it. Now, if there was nothing but a positive up here, then I would go, oh, it's got to be the positive one because more than likely it's not the negative. But if you ever see negative signs, that's kind of the red flag for, well, it's possible that it's positive. It definitely could be negative. But with this logic, it's kind of like there's nothing really that convinces me that this thing is 3.6. I mean, maybe a little bit, like root 5-ish is about 2-ish, and 5 minus 2-ish is about 2-ish. So it doesn't even look like 3-ish, but it's really not 5, it's less than 5, maybe like 4, after you subtract all that junk from it, and root 4 maybe about 2. That kind of makes sense that 5 minus 2 would be next to 3, but I just know that it's not 8.4. So usually with some logic like that, you should be in good shape.
Wait, how do you know it's not equal for a kind of?
Again, like right here, 5, you're subtracting you know that square roots give you positive numbers, right?
Mm-hmm.
So all this is positive. So when you go 5 minus a positive number, it's got to get smaller in value, right? Now, if I was minusing a negative, subtracting a negative, that could go up, but I'm subtracting what can never be a negative. So there's no possible way for this to ever increase to the point you would get 8.4. It's got to go down. Yeah. So that means I have to go with the other one. It's kind of like a multiple choice test where you don't know the answer we talked about, but you know it's not the other ones. So I know it can't be this, so by default, it must be that. So I'm usually using logic like that because it's really hard to actually find that if it goes forever. Right? So we're trusting the algebra here that it works, but it still is a little shaky, I know, in your gut. And if you're also looking at this and saying, man, that 2 really got me, I don't think that I'm going to be that subtle on your test. I usually am a little bit more direct. I mean, I'm not trying to get you to miss an entire problem because you just carelessly forgot a 2. I'm trying to check your ability to do the math. So if I'm going to do something different, it's probably something a little bit more obvious like this. Are you all with me? But expect to see like a little outlier like that where you're like, oh, the 5, other than the 5, it looks great, right? 2 root 3, 2 root plus 2 root 3. So that's probably more along the lines. The other problem that we just did was I thought a little sneaky. All right, so I doubt I'm going to do that on a test because, again, I'm trying to see your understanding of it. All right, so did that help you here with the plus minus? Okay, so let's look at the review number 15. Okay, so on this number 15 right here, it says assume each variable represents a positive number. Now the reason why that was spoken was because, like, do you remember learning that the square root of y to the 5th is the same thing as like a y squared, and a y? So each time I take the square root of that y squared, I technically get absolute value. And since I'm doing it twice, I have two absolute values. But there's still that root y left over. Now, on this particular one, the absolute value is going to make that y positive, right? But so is the square. So on this particular one, I could go, you know what, I really don't need the absolute value. I could just write it as y squared root y. And that's what I would do on a problem like this. But here's the thing, on this one, right here, and because I already, like on this, because I already have a y on the outside, now I end up with y cubed root y. But on this problem, if I don't say that each variable represents a positive number, on that one, what's going to happen on a y to the 7th? Let's take a look. On a y to the 7th, that means I have this underneath. And if I have 3 of those, I got to bring all 3 of those absolute values out with one left over y. But this time, can I get rid of the absolute value? No. Well, that would leave me with some, over here, that would leave me with like a y cubed root y with a number out here. And an I, by the way, because they're negative. And over here, I'd be left with an absolute value of y cubed, I, with a root y. Well, how do I add those? Well, the short answer is I don't, because I don't have like terms. But what if I come along and say, hey, each variable represents a positive number? Then what do you not have to worry about? And now I can add them. So they were trying to make a tricky problem on your homework. I just used the example and used the wording from the homework. So if you did your homework, you ran into that at some point. And they were just trying to see if you could kind of simplify something really ugly. This one has an I, but look, you're going to end up taking an I out of there and an I out of there. And this one has one y, no y, and y squared on the outside. But here, by the time you take one y out of that, and 3 out of that, and 2 out of that, now you have this big expression with like terms. And you're going to notice this, you can take a 4 out with the 3 left over. You can take a 2 out with the 3 left over. And this ends up being, a 6 out with the 3 left over. So you end up with a really big like term expression. And that's the way they allow you to do that is just say, hey, you don't need absolute value. And that's the wording they use. And it's possible, I have given a question like that before, since you saw it on the homework and now you're seeing it again, but that was the idea of that. Are y'all with me? And then, so that's number 15. The key is on if you want to check the key on that. Absolute value. So absolute value was addressed in number 19. We didn't spend a ton of time on that, but I'll go over the why again. Do you remember that you can graph absolute numbers like this? Do you remember that? Because this has a real part, and you know how to graph -2. You go over here and mark -2. That's the number -2 on a number line. And you normally just draw a number line because it's a real number line. But if I introduce an imaginary component, then I have to stretch up here. So this is not x and y, this is real imaginary, but it's similar. So the imaginary component tells you to go up 5 on the imaginary axis. You didn't know there was an imaginary axis before a couple days ago. But that says, okay, well, I'm not going to stop at -2. I'm going to go to -2 and then from there up 2, 3, 4, 5. And that represents -2 on the real, +5 on the imaginary, or the number -2 plus 5i. Well, if all of a sudden now I ask you for the absolute value of it, because they're just naming it z, okay? It's like, I'm a human being, I have a name. That's an imaginary number, it has a name. And they're saying, hey, what's the absolute value of that particular imaginary number? That's all they're asking. Well, the absolute value, remember your old-timey definition. Your old definition you originally learned was the distance from 0 on a number line. So the absolute value of -2 was that length right there, right? Now, the easy way to do absolute value of a number like that's just to throw the negative away. But the real way you're doing it is measuring that distance. So if my point is not here or there, but it's out in space, How do I measure that distance? Well, I look at the triangle made from the movement. I went -2 that way, +5 that way. Can you use something to find that length? And that's how you take an absolute value. So all you really have to do is think Pythagorean theorem. I would have said that length right here, distance, whatever you want to call it, I would have said d squared is -2 squared plus 5 squared, and then I would have square rooted it. Well, if you think about the math of that, all I'm doing is square rooting the real part, which is always going to end up positive, and then adding it to the square of the imaginary. Now here's where people mess this up. They put 5i in there. But that length was not 5i, that length was 5 on the I-axis. I don't put -2r for real, right? Well, I'm not going to put 5i for imaginary. I'm just going to put 5 in square. So make sure you don't put 5i or it ends up being negative when you square the I squared, right? And then you end up getting a square root of a negative, which makes no sense. So your length or your absolute value ends up being root 29. And then later on you see a problem where they go, well, what are the absolute values of all these random numbers? They give you one of these, they give you something like that, and they give you something like that. So, they're real quick, easy, but think, if I have to, use this definition on all of them. Let me show you how you can do that. Like right here, I don't think anybody has any issues with -4, right? What's the absolute value of -4? 4. Now, if you think about -4 as -4 plus 0i, then when you do this, square the -4, square the 0, and then square root it. And you get 16 plus 0 is 16, square root of 16, extra 4. Right? What about this thing? Can anybody eyeball that and tell me what the absolute value would be? 5. Because if you graphed it, think about it. There's no real part, so you're going down 5. That's -5i. How far is that away from 0 on the number line? 5. So you can throw away negatives just like you can throw away i's and just say 5. But if you didn't know that, how could you use this definition? This number's really what? 0 minus 5i, right? So couldn't you say 0 squared, -5 squared, and then square root it, and you get 0 plus 25 is 25 squared, 25, there's your 5. And then this one, you just have to use it. So in this case, you're like, oh, that's right. I know that that's -2 down 7, that would make a triangle. And to find that length, I'm going to square the -2. I'm going to square the -7, not the I. I'm going to add them together, and I get root 53, which is 7-ish. And that's absolute value. But don't, for the love, don't just go, oh yeah, make it positive. That tells me you have never learned this. I have people do that every year. They go, +2 plus 7i? Now they may have learned it and just forgot it, but more than likely they just didn't learn it. All right, so that's absolute value, and then a rounded, infinite, and repeating. We did one of those.
What about like the z-bar part?
Okay, yeah, z-bar just means conjugate. It's just a definition. So, but yeah, and that is what it's called. So the conjugate of that would be what? Actually, you keep that the same and just change the middle sign.
Do you always keep the first one?
Yes, always keep the first the same, change the middle sign. And that just means the conjugate of this. So just, yeah, keep the real part the same, change the sign of the imaginary part. And then, I'm happy to do one of these infinite repeating ones, but since we just did one, I'll probably hold off and wait until we're done. Rationalizing cubed roots. If you look down, I'll tell you what, I'll use some different problems, but for example, do you remember like if you have a square root, like root 2 minus root 3, those are square roots, what do you multiply by? To rationalize that denominator. Root 2 plus root 5. And the reason why is this is kind of like an a minus b. You'd multiply by an a plus b. And when you do that, what happens when you FOIL it? All those middle terms cancel, right? That's why you do it, because this gives me a squared minus b squared. And the great part about that is I'm basically, if that's my a and that's my b, by doing this on the top, the conjugate on the top and the bottom, I'm squaring each of those, but all the middle terms cancel. So I don't have to deal with radicals anymore. That works great for square roots. But what happens when they're cubed roots? On a cubed root, I want to end up with something cubed. And this doesn't work anymore, does it? So what do we do with something like that? What do we multiply by so that we end up with the difference of cubes? It's not even a binomial. What is it? That's right. So this ends up being a trinomial, basically on the numerator and the denominator. And what is that trinomial? Well, you got to remember how to factor these.
It would be 2 squared.
It'd be what?
Well, a squared
Yeah, that would be the a squared,
plus
b squared, and then yes, plus and plus. And why? Because that's opposite sign, and the last one's always positive. So what goes in this trinomial here to make this work? I'm going to have to square that, which gives me cube root of 4. I'm going to have to square that, cube root of 9, right? And then I got to multiply them for the middle term, cube root of 6, and the signs are opposites, always positive. And then, of course, whatever you do on the bottom, you have to do on the top to keep the algebra in play. And that's what works. And I don't even bother foiling this, because if I foil it, I've got 6 terms I've got to write out. What are the only 2 things that are left? The a cubed and the b cubed being subtracted. So I'm just going to go, hey, first times first, last times last, all the other stuff in the middle goes away. So when I do that, I get that times that is cube root of 8, 2. And then negative that times positive that is cube root of 27, which is minus 3. And then I am going to have to multiply the top out. So 5 cube roots of 4 plus 5 cube roots of 6 plus 5 cube roots of 9. But all of that's going to be over a negative 1. Are you seeing this? So if it's all over a negative 1, I multiply the top and the bottom through by a negative, and I'm done. And that's what I would do to rationalize a cubed denominator that was a binomial. But is it possible that binomial is a trinomial? Well, if that's the case, then you got to go back and multiply by the binomial part. So I'll just give you a little whiff of that to make sure you're with me. So what if I started you with this? Minus. So do you see what you're given? This is the what? Yeah, so this is kind of like the a squared term. That's like the b squared term. That's like the ab term. Negative plus. Well, what would make that work? What would be the binomial there?
a plus b.
Yeah, you just want the a there and the b there, and then the opposite sign. So if that's the a squared, what would the a be? Not cube root of 5 squared, but cube root of 5.
How did you get that?
How did I get what?
Cube root of 5.
Because that's cube root of 5 squared, right?
Oh.
That's the squared part. I don't want the squared part, I just want the regular part now. So I just want the cube root of the regular 5. And if this is the cube root of 2 squared, for the b squared, I just want the cube root of 2. And if this is negative, I want the opposite sign, must be positive. And then of course if I do it to the bottom, I got to do it to the top. And what's going to happen when you multiply all this junk out? You're going to get 6 terms. The 4 middle ones are going to cancel, and all that's going to be left is first times first. So that times that's cube root of 125, 5. And then last times last is positive cube root of 8, 2. And I end up with 7 cube root of 5 plus 7 cube root of 2 over 7. And then all those 7's cancel, and I get cube root of 5 plus cube root of 2. That could totally be on there. And then one thing, guys, this is probably one of the easier things on this test, and I mentioned it a bunch when I mentioned it, but it's been a few days. But I'm going to ask you, and then I'm going to really emphasize something. Where does an I come from?
Square root of
What kind of root?
square root.
A square root. The only time you get an I is if it is a square root of a -1. Now, you can totally get an I from something like the square root of -8, but it's because that's the square root of a -1 times like a 4 and a 2, and the square root of the -1 is an I, the square root of the 4 is a 2, and you have a root 2 left over. So that's possible, but that's just a square root. Any other root that it's not squared doesn't give me an I. So if you had something like the cube root of -8, what do you do with the negative? It's just a -2. And if you're looking at it and going, why? Well, couldn't you think about that as the cube root of a -1 times an 8? And couldn't you think about a -1? Isn't a -1 the same thing as that? Isn't that still -1? And isn't a cube root of 8 the same thing as that? And on cube roots, you can just cancel them. You don't need absolute value unless it's an even root. That's why you end up with a -2. Now, don't go through all of this mess. Just do this. Oh, cube root of 8 is 2. Don't take an I out, take a negative out. And if it's a fifth root of like a -32, if it's odd, take a negative out. Cube root of 32 is 2. The only time you take your eyes out to see more clearly is when it's a square root. And you don't see the square there, so it would be like a root that you know is a squared root. Y'all with me on that? I kid you not. I probably emphasized that more this year than ever before. But I mean half of my students last year. That's a group that had, 13 national merit semifinalists, most in history. Half of them missed that and pulled an eye out. And I said it this many times. So be aware of that. Don't just get, I know it's great when you're like, hey, take my eyes out first, I'll see more clearly. And you go through them, you keep taking eyes out. But only do that when it's a square root. And if you happen to be thinking, well, what would that mean if it was a fourth root of a negative? Well, first of all, you will not see that in this course, in this school, at any time. But to answer your question is, a fourth root is technically the square root of a square root. So technically, this inner square root of a -1 is an I, so you end up actually getting the square root of an I. But you won't have to know that in here. So just don't worry about it. All right? Another way I guess I could prove that, is think of this as a -1 is the same thing as an I squared, isn't it? Right? Because if you had an I squared, you'd replace it with a -1. And then do you remember how you can, I mentioned it once or twice before, how that 2 and that 4 could be rewritten like this? I to the 2 over 4, which is I to the 1/2. And technically, I to the 1/2 is the same thing as the square root of an I to the 1st. So that's another way. But guys, again, you will not see that. You'll see square roots of negatives like this, and you'll see odd roots of negatives like that. You will not see higher even roots of negatives at any point in your high school math life. I don't even have a memory of seeing them at like a math tournament, although I'm sure it has happened over time. And then that's it. Anybody else? Yes?
I have a question. So doing the absolute value of z stuff, like on number 24, it's problem that's the absolute value of 5 minus 2I root 3. So how would the root 3 change?
That's part of the imaginary part. The imaginary part is the part that's with the I. So even though I write the I in front of it for good form, that is your real part, and then all of that is your imaginary part. So the rule is square the real part, square the imaginary part, square root the whole thing.
Okay.
So yeah, so for this you'd have 25, 4 times 3 is 12, add them together, root 37. So just a little bit more than 6. So yeah, don't let that bother you a bit. It's just everything that's with that I is the imaginary part. Just don't make the mistake of bringing the I down, or you're going to square an I and it's going to be negative, and then you're kind of breaking up your logic on your triangle. Because now your lengths are off. You're not doing the Pythagorean theorem anymore. And what are you always going to do on a problem like 27 when you're finished and you have your answers?
Check.
Check them. Just take the time to check them and make sure you're okay. Anybody else? Anybody? All right.